Hello students. Dear students, we have been learning very important chapters of organic chemistry. In previous lecture, we have completed alcohols and phenols of their preparation methods, structures, physical properties and chemical reactions of alcohols and phenols. Today we are going to learn in detail about ethers, their structure, preparation methods, chemical reactions and important questions of ethers. Dear students, what is ether? Ether is a compound which is having oxygen bond in between alkyl or aryl groups. For example, if I take dimethyl ether or methoxymethane, this is a symmetrical ether which is having sp3 hybridization of this oxygen, and this dimethyl ether is having sp3 hybridization and the shape of this molecule is tetrahedral and the bond angle is little higher than the usual tetrahedral. Usual tetrahedral bond angle is 109.28 minutes. However, because of these two bulky groups, so instead of this in this way tetrahedral usual manner, it is repelling. So because of this repulsion of these two bulky groups, the usual bond length is higher than the usual bond length of sp3 hybridization, and the bond length between carbon and oxygen is as usual same as in alcohols where it is 142 picometers. In ethers it is 141 picometers. Let us see what are the different types of ethers. We commonly come across symmetric ethers, symmetric or simple ethers, or mixed or unsymmetrical ethers. That means the ether is going to have different groups. The usual nomenclature follows whatever the group here it is, whether it is alkane or aryl group, take the name of that group, at the same time add ether at the end of the name. For example, symmetric ethers: methoxy, methane, C2H5O, C2H5, ethoxy, ethane. This is mixed ether, and the IUPAC nomenclature follows like this. For example, this is dimethyl ether. The common name is dimethyl ether. This is diethyl ether or methyl isopropyl ether. Whereas the IUPAC names are like this: methoxy, write the name as methoxy, methane. There should be no gap between methoxy, methane. Then ethoxy, ethane. Whereas this is a mixed ether where one side alkyl group is methyl and other side alkyl group is isopropyl group. This nomenclature follows like this: 2 methoxy propane. Like this the nomenclature follows. Let us take some aromatic compounds. This is one of the mixed ether where one side is aryl group, other side is methyl group or alkyl group. This is common name is anisole, and the IUPAC name is methoxybenzene. When it comes to ethoxy, same way you can nomenclate: C2H5 phenol. The common name is phenol. However, it is rarely we use in the reactions. Anisole is a common reagent or a starting material for different types of reactions. So phenol, it is ethoxy benzene. Let us take one cyclohexane ring. The nomenclature of this, if I ask you to write C2H5, then where the numbering starts? Dear students, the gem dimethyl group gets the priority over this oxygen or ethoxy group. So the IUPAC name follows like this: 2-ethoxy 1,1-dimethyl cyclohexane. So this is how you can nomenclate. Usually ethers are symmetric where two sides groups are same. So methyl group, methyl group. Here ethyl and ethyl same. Here it is mixed where one side group is different and other side group is different. So these type of ethers are known as mixed or unsymmetrical ethers. For example, methoxy benzene, which is commonly known as anisole, and the nomenclature, these ethers nomenclature follows methoxymethane, ethoxymethane, 2-methoxypropane, and whereas the common names are dimethyl ether, diethyl ether, yes, methyl isopropyl ether, and methoxybenzene or anisole or methylphenyl ether, like the common names. Yes, students. So what are the common preparatory methods of these ethers? Let us see. Yes, students, preparation of ethers. So usually there are two methods. One is dehydration of alcohols, and the second one is Williamson synthesis, which is very important synthetic method for the synthesis of ethers. Williamson's ether synthesis. Let us see one by one. The first method, let us take ethanol, for example CH3, CH2, and this is alcohol. When I treat it with sulfuric acid, say usually concentrated sulfuric acid or H3PO4 you can use. So if I use sulfuric acid, it is temperature dependent. At 170 degrees centigrade, at high temperatures, it undergoes elimination reaction to give alkene. So which is not required to us, alkene, because of elimination reaction. Then how to make this? At lower temperatures, yes, you can get at about 140 degrees centigrade, you will get, let us take 2 moles of this CH3, CH2, O, CH2, CH3 plus this water molecule. Dear students, this molecule is diethyl ether, or I can name it as ethoxyethane, or the usual way of writing this diethyl ether is like this, diethyl ether, or I can write ETOET, or I can write the same compound C2H5 O C2H5. These are all the usual methods of representing this diethyl ether, which is a common solvent used in organic synthesis. Yes. So diethyl ether, in olden days, this diethyl ether used as anesthetic solvent. However, because it has some central nervous system effect, now it is not used for anesthesia. However, this diethyl ether is very common solvent in organic synthetic laboratory. Yes, students. So what is the mechanism? How it is going to form diethyl ether. So these are all the methods. I can write in any one of these methods. So since we are using H2SO4, it is giving H plus ions, and we know that the oxygen is going to have lone pair of electrons. So this alcohol is going to take up proton to give CH3. Oh, hydrogen already is there. New hydrogen has come here, and now what is the charge? Oxonium ion. This oxonium ion, now what is going to happen? Under SN2 reaction conditions, SN2, where it is a primary alcohol, SN2 nucleophilic substitution, bimolecular nucleophilic substitution takes place, where another molecule of alcohol enters from backside. Yes, so this is what is going to take place. It is going to attack onto this hydrogen, and it is going out as water molecule, minus this is water, and what is left over? Here it is CH3, CH2 and O. Hydrogen is present here, plus and CH2, CH3. Now it is very simple. It loses hydrogen minus H plus ion. Yes, so here whatever is added here, it is coming out. So CH3, CH2O and CH2, CH3. So this is how I can prepare diethyl ether. This is common method, but what are the shortcomings? What are the difficulties in this method? Yes, simply take the alcohol and add sulfuric acid. You are going to get diethyl ether or some ether. But it is having some shortcomings. Demerits of this method. What are the demerits? It is SN2 reaction. If I take here secondary alcohol or tertiary alcohol, it is not going to give ethers. It is going to give elimination products. So secondary or tertiary alcohols are not useful in this method, because these secondary and tertiary alcohols are going to undergo elimination reaction to give alkenes. For example, if I take here tertiary butanol, so at this stage it easily loses water, and the formed carbocation easily takes up this proton and gives elimination of this. It is going to give, this is the unexpected or unwanted product. Yes, so this is propene we are going to get. 2-methyl propene we are going to get. So this is one demerit. And even if I want to make diethyl ether with sulfuric acid, the temperature control over temperature is not there. Temperature control. So we have to shift if I heat 140 degrees to 170 degrees, you may not have that much control on reaction temperature. So if I just increase the temperature, we are going to get this, but it is not required to us. We are specifically required this diethyl ether. So this is another drawback. And the third drawback is mixed ethers. Mixed ethers, that is, for example, if I want to prepare CH3, CH2, OH plus CH3, OH, that means CH3, methoxyethane. If I want to make methoxyethane, I have to take the mixture of these two alcohols. When I treat it with sulfuric acid, which alcohol is going to give this ether? There is a chance of giving this diethyl ether 1, and chance of giving this, and there is a chance of giving dimethoxy this dimethyl ether also. So if I want to make mixed ethers, I am going to end one diethyl ether this and methoxyethane and methoxymethane. So three products I am going to get mixture of these three products. So that is why this method usually, yes, you can use it for the preparation of specific ethers. However, it is generalized method. It is not possible to make different types of ethers because of these drawbacks. So what is a versatile method for the preparation of ethers is Williamson's synthesis. Let us see. Yes students, Williamson synthesis is like this. Take alcohol, make the salt of alcohol just by treating sodium, for example RONA, then to this add alkyl halide to give sodium bromide. So this is the ether we are going to get. Yes, it is very simple and a versatile method for the preparation of alcohols, ethers. Let me take one example and explain. This is tertiary butanol plus methyl bromide in presence of sodium. I am going to get OCS3. So what is the mechanism involved here? What is going to happen? As usual, yes, first make this alcohol into sodium salt to give sodium tertiary butoxide. It is a mild base. So since it is H plus, yes, I have explained how alcohols make salt with sodium. So it makes salt with sodium, and here it is going to have partial negative and this is partial positive charge. Now when I add methyl bromide, what is going to happen? This is negatively charged. It is going to out and this comes in to give this ether which is required or which we are in expected compound. O and this is methyl. And the leftover is sodium and bromide. And since it is very versatile and simple method, then what are the case or what are the important things to be kept in mind while doing this type of etherification? So this method is known as etherification of alcohols, I can say, right? So though we are making ethers, mixed ethers, and it is etherification of alcohols. In this case, the important thing is that you have to choose the tertiary or secondary alcohols as alcohol part, whereas this side it should be primary halide, primary alkyl halide. Otherwise, what is going to happen if I take this side, for example, bromide plus methanol, you may say like this also. So am I going to get this? No. In presence of sodium, sodium methoxide is going to form first. So what is going to happen? Sodium methoxide. This sodium methoxide is base also. It is in alcohol solution, that is methanol is an alcohol solution. And it is a base, strong base, alkyl halides in presence of alcoholic base undergoes elimination reaction. Why? It simply take up goes out this bromine and it is going to form positive charge. This CH3, this CH3 and this CH3. Now this is stable one. Instead of allowing this molecule, since it is tertiary compound, it is not going to allow this molecule. It simply loses one hydrogen, minus one hydrogen. It gives double bond CH2 and CH3 and CH3. Yes, and the leftover is methanol will be as it is. So the wise idea or wise method of preparation of this Williamson synthesis is choose the alcohol part as tertiary or secondary if you want to make these type of alcohols. Otherwise, if you want to make symmetrical alcohols, no question, you can take any of these and do. Yes, students. So let us take one aromatic example and you will come to know what I am saying. Yes, students. So here if I take phenol and take methyl iodide or bromide, methyl iodide, and the modified series of Williamson is I can use potassium carbonate and acetone as a solvent. I am going to get methoxybenzene. This is one of the usual methods for the preparation of anisole plus this is potassium carbonate is going out as carbon dioxide. Yes, right. So what is left over? The mechanism, or I can use methyl bromide or methyl chloride. So here the common usual method I can use is sodium. Let me use the same sodium. I don't want to confuse you. Sodium, here sodium bromide, it is going out. I can use methyl iodide, methyl bromide or methyl chloride. So however the reactivity order is like this. Methyl iodide going to react very fast, then methyl bromide, then methyl chloride. Yes, and moreover methyl iodide comes as liquid at room temperature. So usually we use methyl iodide. What is mechanism here? It is very simple. It is going to form this here and it goes out. So this is how Williamson synthesis is very versatile and important method for the preparation of these ethers. Then question comes, if I take this side iodide and use methanol and use same sodium, am I going to get this? So this is methyl part and this is methyl part, this is oxygen, this is oxygen, and here phenyl iodide, iodobenzene. Yes, you will get iodobenzene. Is it possible to make this? No. No, because the nucleophilic substitution on this carbon is not allowed or is not possible. Yes, formation of this alcohol on these bonds sp2 hybridized carbon with this oxygen is not possible. So this method will not work. You may get this type of questions. So give the starting materials for the preparation of this anisole. Yes, I can write whatever may be the starting material here. I can put bromine also here. I can put bromine here. Right? So you may get doubt now. And so this, if it is the starting material, this and this, what is the product? This is how you will get the question. However, it is the usual way is phenols will not break this bond because this oxygen bond is going to be double bond like character. Yes, I have explained in phenols chapter. So this is why. That is why use phenol as starting material and whatever the other ether you want to make, use this side. For example, if I want to make this benzyl oxy benzene CH2, I can write phenyl here. So can you suggest the starting materials here? Yes, students. So the starting materials are phenol plus this side CH2 bromide, benzyl bromide I can use. So this is how you can prepare phenols, usually in two methods, where use of alcohol and do the dehydration using sulfuric acid, where it has some drawbacks, whereas Williamson synthesis is a versatile reaction where you can make symmetric as well as mixed ethers. Yes, students, let us see the physical properties of the ethers. Yes, students, so what are the physical properties usually we come across? It is boiling point or melting point. However, the common ethers we come across are liquids. So stick on to boiling point. These boiling points are increases as the molecular weight increases. At the same time, boiling points decreases as the branching takes place in one of these, any one of the alkyl or aryl chain. Branching increases. Yes? So these are the common trends followed by ethers. And this is common to all types of molecules also, where we have come across in alcohols and phenols, hydrocarbons and all. Right? This is a common trend where branching decreases the boiling point. These boiling points are nearly comparable or same to hydrocarbons. Means, for example, the molecular weight, if I take the pentane and diethyl ether are very near to each other, and whereas this N-butanol, if I take N-butanol and the comparison between pentane, diethyl ether or N-butanol, the boiling points, these two alkane and diethyl ether boiling points are very near to each other. Its boiling point is nearly 36 degrees centigrade. Dear students, in some textbooks, the boiling points or the temperatures are given in Kelvin scale. However, in higher studies, the Kelvin scale is not going to be used. In publications also, Kelvin scale is not going to be used, right? So in published text, in published international publications, we'll use degree centigrades. That is why I am teaching in degree centigrades. For example, if I want to show this temperature in Kelvin scale, it will be like this: 309 degrees and 309 K. So this, the number seems to be very high, and you know the degree centigrades, it is very easy to remember. 0 degrees ice temperature, 100 degrees centigrades boiling temperature of water, like this, so that you will come to know what is the range of temperature. That is why I am teaching in degree centigrades. However, in textbooks you will find in Kelvin. Don't confuse. So I am sticking to centigrade scale. Yes, students. So you can convert if you want to Kelvin scale, but the easiest and the best way to sit in your mind is degree centigrades. That is because you know the temperature of 0, that is ice temperature, and you know the temperature of 100 where water boils. So This is how 36 degrees centigrade. It is very near to just above the room temperature. The room temperature usually is 25 degrees centigrade. And diethyl ether is 32 degrees centigrade. That means in room temperature you have to keep it cold. This diethyl ether has to be freezed or should be stored in a refrigerator at 5 degrees centigrade. Right? Otherwise, slowly it evaporates at room temperature. So when it comes to N-butanol, its temperature is about 113. That means the boiling points of ethers are nearly comparable or same to hydrocarbons, whereas the boiling points when compared to alcohols, boiling point is very high, whereas ethers low boiling point. Low boiling point of ethers. Why alcohols are going to be very high boiling point? Because presence of hydrogen bonding, that I have explained in alcohols chapter. Hydrogen bonding. Yes, so this is one phenomena. And one more phenomena, it is said in your some textbooks that ethers, when it comes to ether solubility of ether, let me stick on to diethyl ether in water. Yes students, it is when practically see, yes, it is soluble about 7.5%. Means if I take 100 grams of ether and dissolve in 100 ml of water, it is going to dissolve only 7.5 grams and remaining is insoluble. Right? Whereas this N-butanol, same about 8.5 grams it is going to soluble. Generalized method, keep in your mind that diethyl ether is not soluble. Don't stick to this 7.5%. Diethyl ether not soluble in water and it gives layer. Suppose if I take diethyl ether and water in a separating funnel, water is going to be down and the diethyl ether is going to be upper layer. Yes students, this I am stressing because in some textbooks it is given that it is soluble in water. How come? No. Ethers are, especially diethyl ether is insoluble in water. That is why this diethyl ether is commonly used in organic synthesis to extract the compounds from water. And it forms layer. Two layers are separable, water and diethyl ether. So, I can say that it is insoluble. Don't stick onto this how much percentage it is going to be soluble. So, this simple miscibility is not going to affect. Right? If it is qualitative analysis, then you can say that 7.5% it is going to be soluble. But in general, diethyl ether is insoluble or immiscible with water and it forms layer. It is very, very important, students. Please keep in your mind in your higher classes or during your research also, it may be useful that ether is insoluble in water or it forms layer. Yes students, then comes chemical reactions of ether. Let us see, dear students. So we are going to learn chemical reactions of ethers. Dear students, please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. Let us see the chemical reactions of ethers. So what are the common reactions it come across is the bond which is present in ethers is R, O and R. And the cleavage of this one chemical reaction is cleavage of oxygen and carbon bond. What is this reaction? It is nothing but de-etherification, or if it is methyl group, then if it is phenyl group, then it is known as demethylation of ethers or demethylation reaction. Then how to do? Yes, students. So demethylation takes place under drastic reaction conditions. Drastic reaction conditions means high concentrated hydroiodic acid or HBr or HCl at high temperature, it is going to give or OH plus or iodide. If I use iodide, and the demethylation or the deetherification capacity is HI is going to be very high, means it easily cleaves this bond, whereas HBr is better than HCl. However, the usual method is using hydroiodic acid HI. At high temperatures, it is going to cleave the ethers, right? So, which ether is going to be cleaved? For example, this is the ether. Which side is going to be out? So when I add HI, what is going to happen? Just guess. And another example, if I take simple CS3 and CH2O CH3. So if I take this methoxyethane as an ether and do the reaction with HI, what I am going to do? The first step is, since it is ether is going to have lone pair of electrons, it is positively charged and this is negatively charged, and it takes a proton to give the intermediate of this CH3 CH2O, and CH3 is here hydrogen has come. So in this case, the methyl group is very easy or unhindered. This side CH2, CH3, and this is having positive charge. So what is going to happen? This iodide molecule entering onto this carbon or this carbon, which is very easy to enter this side or this side. So this carbon is hindered, right? So this carbon taking up by this carbon is very tough compared to this, so easily it forms bond with this, right? So this is going to out as methyl iodide, and here it is going to like this plus, and this is OH, and the remaining is CH2 CH3. That means the bulkier group, whatever the ether you take, bulkier group is going out as alcohol, and the smaller the molecule, the smallest part, the smaller alkyl group or smaller alkyl group is going out as iodide. However, if I use excess of HI, even this ethanol, if I use excess of iodide, hydroiodic acid, it takes a proton and it is going to form CH2 CH3, and OH is already there and another iodide, and this also at this stage, just now what I said, at this stage this iodide enters into this to give CH3 CH2 iodide. Yes. So what is going to form from this methyl and ethyl ether, methoxyethane? The products are, these are the products, methyl iodide and ethanol. Then the question is here. So just guess the products from this reaction. Yes, you can say that since it is a bulky group, in this example what I said, bulky group, it is going to break here. But it is not so. Not so. Because this case it is a primary carbon. But this carbon is tertiary carbon. What is going to happen? No doubt it is going to form this. At this stage, O, hydrogen is here, methyl group, and this is a positively charged, and this is methyl and methyl. Yes. So Is it possible tertiary compounds undergoes SN2 or SN1 substitution? SN1. SN1. Right? So SN1 substitution takes place. So at this stage, what is going to happen? It will be easy to lose this and to form tertiary carbocation, which is stable carbocation, right? And the remaining is methanol is this side, OH, and this tertiary carbocation may undergo elimination, right, to give propene, 2-methyl propene. Yes, students? So this is how demethylation takes place. However, to simplify, let us take one aryl methyl ether and you will enjoy the demethylation reaction. Yes, students. Let us take one aryl methyl ether. What you will enjoy? This is OCH3. And let us take one more example, OCH2. This benzyl methyl ether. And when I add HI here, what is the product? When I add HI and heating, what is the product here? Yes? So guess, is it easy to break this bond? No. So just rule out. This bond breakage is not going to take place. This bond breakage is not going to take place. Then what is left over? The methyl group. This is positive and negative. It takes up this and it is going to form oxonium ion, and iodide part will be there, iodide minus and O minus, O positive. Now what is going to happen? This comes here and this takes up proton to give phenol. So the demethylation reaction is very important, students, in synthetic organic chemistry, protection and deprotection. So demethylation takes place to give phenol and the leftover other part is going to be iodide. Yes, so this is phenol and iodide comes out. When it comes to this, so is it going to break here, here or here? What is your choice? It is very simple, students. It is positive and negative. Let's just protonate this oxygen to give, this is the intermediate, O, hydrogen and CH2. In this example, it is CH3. Just write it as phenyl group instead of writing benzene B group. So I can write it as phenyl group. So what it can follow? Yes, it is easy to enter iodide from this side and loses this, and I am going to get phenol, here also phenyl. So benzyl ethers are also common protecting groups, phenyl, CH2, iodide. Yes, students? So this is how demethylation. The method is deetherification or demethylation, or this is debenzylation. D spelling is important. Benzyl, ZY, not ZOY. Benzylation, debenzylation. So this is benzyl group. So debenzylation can be done using concentrated HI or HB or HCl under heating reaction conditions to give alcohol phenols. Yes. So this is one of the methods of protecting this phenol group. You will learn in higher classes or during research, right? So benzyl group can be deprotected using HI. Yes, friends. So these are one of the chemical reactions. The very important chemical reactions of ethers are aromatic electrophilic substitution reactions. Let us take aromatic electrophilic substitution reactions. So the name itself says this aromatic ring. That means the starting material of the ether must have aromatic ring. So I will stick on to this anisole. The easiest or the best examples to be learned is anisole. The name is anisole. So anisole is methoxybenzene IUPAC name, or methoxybenzene or methyl ether of phenol. So this example, I will take this example and I am going to get this, explain this aromatic electrophilic substitution reaction. And before going into deep, so what is the orientation of this methoxy group? Methoxy group orients the incoming electrophile to ortho or para directing group. That means this methoxy group directs the incoming electrophile to ortho. This is ortho position. This is also ortho position, either of these two sides, and this is para position, right? So this methoxy group or ethers are ortho-para directing groups, similar to phenol. So ethers are ortho-para directing group. Why? You can write the resonance structures to learn how it is going to direct this. For example, methoxy. So it undergoes resonance to form anion. Carbanion forms at ortho position, and the electrophile is electron deficient compound. It loves electrons, so it forms electron dense carbanion at ortho position. Yes, students. Then if I do write further resonance structures, and it forms resonance structure or carbanion at para position, and I can write further. So this is, and another ortho position we are going to have carbanion, and the oxane is all these resonance structures. It is tightly attached to this sp2 carbon, and it is oxonium ion. Now it will be back to this, where it is going to have methoxy ether. This is a double bond, and double bond. So these two are same, isn't it? So these two are resonance structures. So because of these resonance structures, what are the positions it is having? Carbanion at ortho, and this is para, and this is ortho. So it is getting carbanion at ortho and para positions during its resonance structure. So aromatic electrophilic substitution in ethers takes place at ortho and para positions. Let us take one example and see. Yes. So the usual electrophilic aromatic substitution is nitration. Let us take nitration. Same, take the anisole as starting material. And what is the nitrating mixture? Yes. Sulfuric acid, concentrated sulfuric acid, it should be 2 moles, 2 equivalents are 2 moles, and the concentrated HNO3. This is nitrating mixture. These two is known as nitrating mixture. Please remember like this, nitrating mixture. This nitrating mixture generates NO2 electrophile. That I am going to give the mechanism. Electrophile of NO2, and it is going to nitrate, or nitration takes place at 2 positions. What are the 2 positions? This is para plus this is ortho. Do you have any guess which one is going to be more or which is going to be major product among these two? This is para, this is ortho, right? Which is going to be major product or major product? Para position product is a major product, whereas ortho is minor product. Means the yields, if I get 100 grams of this mixture product, in that it is going to be about 90 grams of para and about 10 grams of this meta. Why? Because this group is already bulky, it is bulky group, and this carbon to enter this electrophile at this position, it is repels. So the incoming nitro group also is very big group, right? This big group entering at ortho position is not going to take place that easily. That is why the para is major. Most of the case in electrophilic substitution reactions of aromatic compounds, para product is going to be major. It is a thumb rule. Just remember, it is generalized rule. Most of the cases. So blindly, if someone asks, para is going to be major, right? So para is going to be major if it is ortho-para directing group. And what is the mechanism? Yes, in all electrophilic aromatic substitutions, there will be 3 steps. The first step is generation of electrophile. What is the next step? Second step is formation of carbocation or sigma complex. This is the second step. I am writing a mechanism still. The third step is removal of hydrogen from the sigma complex. So in this case, what I am using sulfuric acid. Let me write sulfuric acid. This is sulfuric acid and HNO3. Right? HNO3. So in this case, sulfuric acid is going to act as acid and this HNO3 is going to act as base, or it takes a proton from sulfuric acid to give HSO3 minus plus, this is H positive charge, hydrogen from this sulfuric acid has come, and NO minus. This loses water molecule and gives the electrophile. This is NO2, or I can write NO2 electrophile. This electrophile, now it is floating in the reaction mixture. What is there in benzene? Yes, we have, this is anisole plus this NO2 is floating. It is there in the reaction mixture. It simply takes up this lone pair electron, and let me write at ortho's position. And this is nitro, it's attached here, hydrogen is here, already one hydrogen, methoxy undisturbed, and this is double bond, and here carbocation. And this resonance structures, if I go on right, it goes out here, positive charge forms here, positive charge forms here, and then comes here, here it is going to form, here it is going to form. So the overall compound, what I am going to get upon resonance structures, so this is the sigma complex. I can write it as like this. The positive charge is resonating in benzene ring, and this methoxy is there, and hydrogen is there, and electrophile in this NO2. This is a common mechanism, students, even for your Friedel-Crafts reaction also. Right? Now the third step is, it is removal of hydrogen to give it is going to give in this case ortho OCS3 and nitro, and same way you can write the para product also. Yes, students, so usually 3 steps I have been explaining in all chapters, but since if you are the first time viewer of this lecture, then don't confuse. So the electrophilic aromatic substitution consists of 3 stages or 3 steps, where generation of electrophile, formation of carbocation or sigma complex, or removal of hydrogen. This is how it undergoes nitration. Now you are clear about nitration. Let us see bromination and Friedel-Crafts reaction. Yes. So bromination. Usually bromination requires Lewis acid, bromine plus Lewis acid, for the generation of bromine electrophile. But this ether or anisole or ethers are highly activating groups, so it doesn't require any ferric bromide type. For example, to generate electrophile bromine, if I give, to generate electrophile ferric bromide is usually used for the aromatic bromination, where it forms bromine electrophile, then ferric bromide Br4 minus. So this is a usual pattern, but it is highly activating group. So in this case, ferric bromide is not required. Not required. Simply take bromine in acetic acid. Usually we will get in acetic acid, bromine in acetic acid. We will get as a solution bromine in acetic acid, and this is going to form, bromination will take place. Bromination is going to take place at para bromo compound and ortho bromo compound. Which is major in this case? Which is major? Same story. So the para is major. This is ortho. Para is major product, whereas this ortho is minor. The same thing is bromine is a big atom or molecule, where this is also very big methoxy group, and entering at ortho position is very tough or hindered. Yes, so hindered. So this major para position is very easy to approach this benzene ring, so that is why it gives major product. Same thing, if it forms 100 grams, it is going to be 90 grams or 90% of this para, and this is 10% of ortho. So this is how bromination takes place. It can be chlorination, it can be iodination also, right? Iodination, it follows different mechanism, but bromination and chlorination you can do in this way, right? Let us take very important chemical reaction of ethers, aryl alkyl ethers, is Friedel-Crafts reaction. So what are the Friedel-Crafts reactions? There are 2 types of reactions. Or it undergoes, Friedel-Crafts reaction is of alkylation and acylation, right? So alkylation can be done under Friedel-Crafts reaction conditions, and acylation can be done under Friedel-Crafts reaction conditions. What is the reagent or the catalyst under Friedel-Crafts reaction conditions? Yes, Friedel-Crafts reaction uses Lewis acid like aluminum chloride. That must be anhydrous aluminum chloride. Yes, I have explained in name reactions. Please go through that if you have any doubts. Friedel-Crafts reaction. Yes, students. So Friedel-Crafts reaction. What is this reaction? It is aromatic electrophilic substitution reaction. It can be asked in some entrance texts that what is the type of reaction of Friedel-Crafts alkylation reaction. Yes, it is also aromatic electrophilic substitution reaction. Yes, so this aromatic electrophilic substitution can be written as right, like this also, right? So let us take alkylation. What is alkylation? Let us take anisole OCS3 plus alkyl halide. It can be bromide, chloride or iodide. So under Freelecraft's alkylation, iodides or for example if I take methyl iodide gives better yields compared to methyl bromide compared to methyl chloride. So which one I am going to use? Let me use methyl bromide. Yes, and in presence of anhydrous aluminum chloride, the usual solvent is carbon disulfide. Yes, its boiling point is around 50 degrees centigrade. Take this carbon disulfide and do the alkylation of anisole. You are going to get the mixture of compounds are this orthomethyl anisole plus paramethyl. And what is the ratio of these two? Yes. So usually all the times it may not be 90-10%, but the usual pattern is para is going to be major. Para and this is ortho. Yes. So blindly you can say it is major. It is exactly not 90-10%. And it is minor. Yes, students. Then another type of reaction, it undergoes Freelecraft's acylation. Acylation, what are the starting materials? So if I take same anisole and react it with this acyl group. What is acyl group? CS3COCl, acetyl chloride. The common name is acetyl chloride. I can use acetyl chloride. The different textbooks giving separate the different names, but I am teaching the common names are the names used in research papers. Yes, so remember like this, acetyl chloride. Yes, acetyl chloride can be used in presence of anhydrous aluminum chloride. What is the compound I am going to get? Acetophenone. Yes, students. So acetophenones we are going to get. This acetophenone is paramethoxy acetophenone and orthomethoxy acetophenone. And what is the ratio? Again, write it as this is major and this is minor. And another key point to teach make you know is, so how to separate these two compounds. Dear students, it is very simple. Write down steam distillation. Steam distillation separates these compounds. How? So this acetophenone is having oxygen, this is also oxygen, and it is very near to each other, so it is going to have some minimum hydrogen bonding. So orthoanisole or orthoacetophenone, methoxyacetophenone is going to low boiling point, and this is para is going to be high boiling point. And the first this low boiling point compound distills out with steam, whereas this high boiling points compound distills out later. And one more thing, why this para is going to be high boiling point? Because of this linear structure, I can say. So in a crystal or in a molecule, if it is a liquid, it is going to be tightly packed, so it is symmetric. I can write like this, right? CS3, so it is straight chain, some linear structure, whereas this is it is different structure, right? So it is not going to tightly packed. It is going to be tightly packed, so high boiling point. Dear students, so this is how ethers undergoes Freer-Crafts reaction. Then your turn. I am going to give some questions. If you know, let me check. Yes, students, during the nomenclature we have learned that C2H5. This name was IUPAC name 2-ethoxy 1,1 dimethyl cyclohexane. Yes. Then if I give this compound, write the name of IUPAC name of this compound. IUPAC name. Yes, students. For example, if I want to make this methoxy nitro compound, shall I use bromine plus methanol or phenol paranitrophenol plus methyl bromide? So which one? This is condition 1, condition 2. Which one is going to form? Say in both the case I can have option to use sodium. So which one is going to give this product? Just guess. And this ethoxy ether, this is tertiary butyl, ethyl, C2H5 is ethyl. When I do demethylation using hydroiodic acid, what is the product? Guess. And this is very simple, you can answer this. So let me write question number 1. This is question number 2. This is question number 3. And the question number 4 is aromatic ring C2H5 when I use hydroiodic acid under heating reaction conditions. What are the products? Yes, students, if you know the answers, please write in comments box so that I will answer you. Otherwise, I am going to post the answers below of this video link. Yes, students, it is very easy to write because the key factor is when you are writing this nomenclature, in this case dimethyl is going to be prioritized. Ethoxy 1,1 dimethyl cyclohexane, and moreover since it is attached to 2 carbons, so that is why it is gem dimethyl group is going to be prioritized. And when it comes to these two, this is nitro, this is oxygen. Oxygen and nitrogen, which is priority group? Oxygen and nitrogen group. Which is priority group? Oxygen. So in this case the numbering started from here, whereas in this case numbering starts from oxygen. So write like this 1, 2. I have given the hint. So write down the IUPAC name. And in this case, when you want to follow Williamson synthesis, what I said, nucleophilic substitution at this carbon is not going to take place. So the best way to follow is this method. Take the phenol and do the methylation, right? And here when I do this type of ethers demethylation, what is going to have? It is going to form alkene. Elimination is going to take place. And this is, so which side? You know the answer. Write down answers. Yes? So dear students, I hope you enjoyed this topic. Please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. We will meet again with a new topic. Till then, bye. Sayonara. All the best. Arigato gozaimasu. Thank you very much. Bye students.